Okay, folks, let's get back into it. So second order circuits, we're going to look at those in detail. We'll probably finish up this chapter. So the next homework we'll be doing, I think it's due in a week, if I remember correctly. We can have do this Thursday. Should I change it? I can move it back a little bit. So I'll move it to next Tuesday. How's that sound? All right. So here's our base form. No longer written as a quadratic, but just written as like a standard if you wanted to go back into the Laplace domain. So we have omega n squared all over s squared plus 2 zeta omega sub n s plus omega sub n squared. And we defined omega sub n, the natural undamped frequency of oscillation, if there's such a thing. Damping ratio, which is a unitless quantity, which will be, if it's an underdamped system, will always be between 0 and less than 1, or so slightly under 1. And then our exponential actually doesn't show up in here, but the way that we can get that is through that equation here. And then when you do the quadratic equation, you end up with this expression here, negative b plus or minus the square root of b squared. All that, you can see how we factored out omega sub n because it shows up in both terms, okay? So this is our base expression that we're going to go to. Any questions on this? Kind of finished with this part last week. All right, so now we're going to look at systems that are considered underdamped. Let me move this off to the side a little bit, or down here, I guess. So an underdamped system is a system such that damping, which is another way to say resistance, the resistance in the system is not small enough to prevent, or not large enough, I should say, to prevent the system from oscillating, having some sort of a natural ring. And we can determine that because of this expression here, right? Zeta is going to be, we said less than 1 for sure. We can actually say less than or equal to 0. That's still considered an underdamped system, but it's completely underdamped. It's no value. And when we do that, we're going to get this undamped frequency. Well, not undamped frequency. We're going to get the damped frequency as determined from this expression here. Why do we get that? Well, let's go back over to here. And remember what we had? We had our root was negative zeta omega sub n plus or minus omega sub n times, let me just go ahead and make sure I have it correct, zeta squared minus 1, right? Those are the roots that we have. So the question is, when are we going to have oscillations? Meaning it's going to ring back and forth. It means it has a sine or a cosine expression. When does that happen? Everybody understand my question? When is your output, whoops, going to look something like this? So it's oscillating, right? So it has a frequency. So when does it have a frequency? When zeta squared minus 1 has to be less than 0, right? Actually, not even less than or equal to, less than 0. Because this term has to be complex, doesn't it? If we want to have a sine or a cosine on the output, we have to have that j term underneath there. So if it's zeta is between 1 and here, we can rewrite this, can't we? So here's our base. We know that zeta is going to be less than 1, right? So let's monkey around a little bit. What's the square root of negative 1 again? J. So can't I factor that out of that expression because they're multiplying together? So when zeta is less than 1, we're going to have a j term up front, which means this is going to be a complex number, correct? And this term right here, that's the damped oscillation frequency. Why is it damped? Because our omega sub n is our undamped frequency, and then omega sub d is our damped frequency. It is going to be reduced, the undamped frequency is going to be reduced by the square root of 1 minus zeta squared. This number here is only going to be a positive number when zeta is less than 1, okay? And so if we go back over here, we can see we factored out the J term as we just described, and here is what we end up with, right? That's a complex expression, which means we oscillate back and forth, and the frequency of oscillation is omega sub d. We only have omega sub d if zeta is less than 1. Okay, very important to see that because we will not have this J term. Everybody understand the math that was involved in that to try to get from how we had originally zeta squared minus 1 to now we have 1 minus zeta squared. And the only way we did that is because our zeta term resulted in that number, the zeta squared minus 1 being a complex number, right? That square root term being a complex number. So our omega sub d is our damped frequency. All right, so let's look at 4 cases of damping. 4 cases means we have to go through all the individual ones. The first case is it's an overdamped system, which means zeta has to be greater than 1. If zeta is greater than 1, then over here, that term is not complex, right? Something greater than 1 squared minus 1 is going to be a positive number. So when you do that in the quadratic equation right over here, negative zeta omega sub n plus or minus, this number here is going to be a number that's real, correct? So it's going to be plus or minus a real number. And this translates to S plus zeta omega sub n minus a times S plus zeta omega sub n plus a. When I do when I want to set up for partial fraction expansion, this is just e to the minus something t, right? There's no J term there. So it's just a regular decaying exponential. There's no complex term. So over here, we have 2 real roots. Overdamped means we have 2 real and unequal roots, okay? So two system real poles, we can also add unequal. Anybody want to see how we can get the roots of those, how we got those numbers, or do you feel pretty comfortable getting those yourselves? Anybody will see it? Okay. I'm lazy, so I will use, instead of using quadratic equation, which you're probably sick of seeing, let's go ahead and go and just do the roots approach, right? So the roots of 1, 9, 9. So the roots are negative 7.85 and negative 1.15. If I want to put those into our original expressions, we take the negative of the roots, and that's where we end up with plus 7.854 and plus 1.15, essentially. You can also do the quadratic equation if you want, but at this point, you're probably, like I said, sick of me doing the quadratic equation so many times, so you can go ahead. So now we have to do partial fraction expansion. You all want to do 3 minutes in partial fraction expansion, or are you sick of doing partial fraction expansion? They're good here? Yeah, so we just have to do A over S plus B over S plus 7.85 plus C over S plus 1.15. And those are our expressions for A, B, C. And we can see now we have a unit step, right? Some value. Then we have 2 decaying exponentials. This is my forced response, and these are my natural response, right? So if I'm trying to draw what's happening from a block diagram perspective, I hit the input with a unit step. Here's my transfer function here, and then my output is as shown here. On a pole zero map, I have two real poles that live in the left-hand half plane, so this is a stable system. No terms that are on the j omega axis or that are anywhere up above the real axis. So again, this is a purely real output, no sinusoid. So I have two decaying exponentials. So when I plot that, the C of t, I get something that ramps up and steadies out, eventually reaches 1, which is our steady state value. Okay? Questions on that? Yes, ma'am. It actually verifies that this system is overdamped, because if it's underdamped, it would look like this. It would ring until it got to steady state. So you know it's overdamped or it's critically damped, right? Either of those cases. My question for you is, how long does it take to reach steady state? Can you tell? Hard? Not exactly. How can you tell we've reached steady state? What was our definition we did last week, Avery? 5 time constants, right? So which one is going to decay the slowest? Because it reaches 5 time constants of the slowest system, right? So can you tell by looking at this? Our best is to go e to the minus t over tau, correct? So this one over here is e to the minus t all over 1 over 0.78, not 0.785, 7.85. If we just set it up to look like e to the t over tau, and this one over here is e to the minus t over 1 over 1.14 or 15. Let's be lazy, right? So tau 1 is equal to 1 over 7.85, and tau 2 is equal to 1 over 1.15. Which one is greater, T1 or T2? T2 is greater. So steady state occurs in 5 times T2. Okay. This one over here dies out in 5 times 1 over 7.85. This one dies out in 5 over 1.15. So it takes a lot more time for T2 to reach steady state than T1. Why is that important to us? Because the pole that is closest to the j omega axis is going to be the slowest one to respond. So if we want a faster system, meaning it reaches steady state faster, we want to move those to the left. Okay, move them to the left, and it reaches steady state a little bit faster. All right, and it was kind of sneaky, but if you look over here, I stopped plotting at about 5 seconds, right, which is about 5 times 1 second, where if it was 5 times 1 over 7.85, it would be somewhere around here is where it would stop, and you can clearly see that it's still decaying away, right? So that's some of the subtle things. If you can look at these things, it tells you a lot. All right, that's overdamped. Let's go to case 2, which is underdamped. Now we have complex roots. Omega n is equal to the square root of 8, and we have complex numbers. And so now we immediately do our standard form. So we do the roots of the quadratic equation, or you can just do roots in MATLAB. And what we end up with is our S plus our real part squared plus our omega sub n squared. We have to stuff our omega sub our omega sub n up top. So that means we need it on the bottom. And now we can go ahead and calculate what our C of t is going to be equal to. It's got our forced response term and our natural response term. Okay, and all we did was change the 9. The 9 is equal to 2 zeta omega sub n, correct? Omega sub n is equal to, let's see. Well, let's just back up. So we know that we can solve for zeta, which is equal to 9, sorry. Nope, not 9. 2. So 2 omega sub n, 2 divided by omega sub n is equal to our zeta term. Okay? Questions on that? We can double check the results. When we go ahead and do that, what we see is we have 2 poles. We have complex conjugate pairs that are above and below, right, the real axis. So this is going to have a sinusoidal representation of our term. Okay? So our plot has oscillation to it, but it steadies out at our steady state value. This is underdamped because zeta is between 0 and 1. Okay?
I've got a question.
Yes, go ahead.
About these two systems, you have overdamped and underdamped. For the overdamped, you have 2 natural responses.
Yep.
Is there ever a case where you have 2 natural responses and it's still underdamped?
No, you would only have this one response, right? Because underdamped means we have a sine wave or a cosine wave. Or, I mean, if you wanted to get technical, remember this ends up becoming e to the j times something t. So
Okay.
you would have 2, but it's hard to characterize something with a j term in the real world. So we convert it to a sine or a cosine, and then that way we only have that one expression.
Okay, so for this system, but it's not having one or multiple natural responses, is that not indicative of whether something is underdamped or overdamped?
Well, we got to be careful because what if we have s to the 5th plus a s to the 4th and on and on and on? We could have up to 5 different responses, right? So we don't necessarily know if some of those other ones are because it's a higher than second order term. So we might have additional terms that are natural in there because we just have a higher order, a system that's higher order than a second order system.
Okay.
So that's underdamped. Undamped is really a very unique case, and that tells me that zeta is equal to 0. What happened to my 2 zeta omega sub n s term? Goes away, which means zeta is going to equal 0, doesn't it? Because if zeta is the damping coefficient, and if it's an undamped system, that means the damping coefficient has to be gone as well. So when we do this, we don't have an s plus 1 or an s plus 2 quantity squared. We only have s squared plus 3 squared. And we convert that into the time domain, we have no decaying exponential. Looking at our pole 0 map, no real part, purely imaginary, and those are on the j omega axis, correct? And so this is a system that'll oscillate forever. It's basically just an oscillating, a crystal oscillator is an example of that. Or if you had a purely LC circuit, no resistance in it, once you energize an LC circuit, then you take the energy source away and theoretically it'll just ring forever and ever and ever. which we know is not true, right? We know that there are no real world circuits that have no resistance, but we try to get as close to possible as having it to be a value of 0. Okay. And there are some cases, kind of unique cases, but does everybody know the measurement of a meter? How do they measure a meter? Use this information, but let's see. We go to NIST. I think it's the wavelength of a specific gas. Let's see if we can find it. It's a type of gas, I believe. Based on the constants of nature. Perfect. Okay, so what are they? Oh, gotta love the history lesson. We were just looking for a really simple definition of what a meter is. I don't care about that. Here we go. Let's see. Here we go. It's the hyperfine transition frequency of cesium. That's how they measure a meter. Now you know, and this is the official one. So it tells you they've got some official measurement device, and NIST, I think it's in Colorado someplace. And it's yeah, so it's the cesium frequency is what it's defined as. That's the official unit length of a meter. And so what that means is cesium is basically just going to oscillate. So you just have that particle, and if it's in a vacuum, right, there's nothing to slow it down. So it just should oscillate forever and ever and ever. So that's essentially how they measure a meter. But that's an undamped example. Completely undamped. Zeta is equal to 0. The last case we'll look at is a critically damped system. And critically damped means zeta is not less than 1. And you can't really be greater than 1, because if you're greater than 1, that means you don't have any damping at all. So you don't have a damping ratio. So a critically damped system means zeta is equal to 0. What does that mean? Well, when we do our quadratic equation, you can see that this is a perfect square, right? It becomes s squared plus 3s. Well, you got to complete the square, I guess, to go ahead and get it. So you end up with s plus 3 quantity squared. When we do partial fraction expansion, we have a over s plus b over s plus 3 plus c over s plus 3 squared. And when we get our terms, we end up, whoop, sorry about that. Don't know how to zoom out. There we go. And when we do that, we end up with our time domain expression here. Why is this critically damped? Because look at my time constants. Tau 1 is equal to tau 2, which are both equal to 1/3 of a second, right? And the reason why they call this critically damped is because you have chosen the exact value of damping so that you have two real poles, but they're perfectly equal to each other. And this system is going to be the fastest system that can respond. Why is it the fastest system? Because remember when we do our quadratic equation, negative b plus or minus the square root of b squared minus 4ac all over 2a. We know that negative b, I'm going to add a number to it, or b over 2, and I'm going to subtract a value, right? This one, because we're adding to it, right, is going to be closer to the real axis. This one's going to be further away. So this is always going to be the slowest, the slowest pole. right? Remember how we said over here, if we get closer to the real axis, it just takes longer to get there. But if this is plus or minus 0, it's always just going to be B over 2. So critical damping is you've perfectly chosen the amount of damping for the system such that it is going to respond to the fastest. And why is it critical? Because if it moves any which way, to the left or the right, you're now going to have a slower system. In the real world, you would love to have a critically damped system. The problem is it never stays that way. Because what happens to real world systems over time? Yeah, their characteristics change, right? Some dirt happens and it's no longer going to have the same operation. And so now your oscillation frequency is going to be slower, right? Or the system's going to respond slower. So with that being said, if you were going to design a system in the real world, we can't do critically damped, right? Because we know that it's perfect when it starts, but eventually it's going to fade away. We don't want to do under damped because we know that that's a really slow system. We definitely don't want to go with undamped because that never reaches steady state. So you would always go with a overdamped system, right? I mean, an underdamped system. Why? Because if the system changes, it's most likely going to be some, fouling of the system. So what's going to happen is this might overshoot, but then it's going to reach steady state faster. So in the real world, you always want an underdamped system because the other three are always going to give you problems. Unless you can do an extensive amount of maintenance on your system and maintain a critically damped system, it's just not viable. And there's something called Ziegler-Nichols tuning or quarter amplitude damping tuning that talks about each successive peak. If you're in a control systems, each successive peak would be 1/4 the amplitude of the previous one. So that's an acceptable level of tuning as well. This is the preferred characteristic that you want. Okay. So our critically damped, we have 2 poles. Those are in the same spot. They just can't be shown on top of each other because you would not see them. So you have 2 at -3, and this system responds the fastest. Okay. Questions on that? Avery. Yep. So same thing. Thank you. That's my forced response. And then these 2 are my natural responses because you can see that they have decay. So those terms go over there, even though this one has 3t. So as time increases, that multiplies, but the exponential is a bigger problem, right? Because it's either the -3t that has a bigger impact on the output than the t does. So here's the systems all put together on one plot. We start out with undamped and look at the amount of oscillation. And these are normalized too, so that the steady state value is equal to 1. An undamped system is going to oscillate forever, and its magnitude is going to go twice what the steady state value would be if it was allowed to dampen out. So it's basically like a DC offset. Then we start adding some resistance, and we moved to an underdamped system. Then adding more resistance, eventually we'll get to critically damped. And then we add too much resistance, and then we are an overdamped system. And you'll notice which one reaches steady state the fastest. It looks like this is steady, approximately there. Look at the next fastest system. Well, we know undamped is never going to get there. But look at overdamped. To get at that same value, it's way out over here. But critically damped, we're here, right? So this is the ideal characteristic, but it's never going to happen. And then eventually, we're going to go to our underdamped system, and then, whoops, into 3, and go to our overdamped system. So you start your characteristic here, and then eventually you move in this direction, and then you start going in the other direction, and then you move back. So in the real world, you would start with position 2, go to 1 if the system was to degrade over time, and then eventually it'd start working its way up to 3. All right, so these are all the different characteristics. Let's see if I can move this on the side here. take a look at a simple system. So find zeta and omega sub n. Well, first thing we do is write and then that corresponds to s squared plus 8s plus 12. We can very quickly see omega sub n squared is equal to 12. So you can solve for omega sub n. And then 2 zeta omega sub n is going to have to equal 8. So zeta is equal to 8 over 2 times omega sub n. So that's how I solve for those values. And now, because my zeta term is 8 over 2 divided by the square root, so it's 4 divided by the square root of 12. What's the square root of 12? It's less than 4, right? Because the square root of 16 would be 4. So we know that this is going to be 4 over something that is less than 4, which means this is going to be greater than 1, isn't it? So this type of a system is a overdamped system. Its characteristic is here. So you just treat this as 2 first-order systems. If you want to figure out when the system reaches steady state, we got to go back to the beginning, where we looked at first-order systems. So we took a look at settling time and rise time. So 2 first-order systems, we just treat it like the work that we did here. Let me show you. Whoop, stop moving. We use these equations here. Rise time, settling time, we use those equations. If it's a second order system that is overdamped, it's just 2 first order systems. Okay? We don't need to use any of the equations we'll be showing you here in a minute. All right, so we'll do this in homage to some of you folks on the test who love doing algebra. This is the way that you can actually do the solutions if you wanted to do it with sines and cosines. So it's a lot of math to make it work, but this is the generic one when you have a system, especially if it's underdamped. And again, we're going to combine that to this expression over here. So we combine that using Euler's identity to go ahead and represent it. So notice we have a theta term added in there, and our magnitude has been adjusted a bit. Here's the expression for theta. And now, get this over here. Thought I had it on the side, I guess. Perfect. You can see how as I increase zeta, look what happens. As I increase zeta, I go from, really high peaks to almost no peaks. And my frequency starts to change. So this here, let's say that corresponds to, whoops. Sorry, I get unplugged. See how long my battery lasts. 35 minutes. That's not good. 35 minutes?
Maybe 45.
Yeah, this is a 3-year-old plus computer, and there's a lot running on it, so it does heat up a lot. So, but you can see it oscillates more, and it oscillates at a higher frequency. So as I start to bring my 0.4, look at how that elongates out, right? So that's 1, that's 2. So it changes the oscillatory frequency of it. Okay. So it gives you a little bit of a characteristic about what's happening with our damping. But more importantly, now we have an expression over here that can use that expression or that equation. Now we can go ahead and calculate those parameters that we were looking for. Rise time. Settling time. Exactly what we had before. But in a second order system, if it's underdamped, we have the ability of overshooting our steady state value. So at this point, we have to calculate how much time it takes to reach our peak time, and then how much does it overshoot our nominal value. So our peak time equation is here. Pi over omega n times 1 minus zeta squared. And then our percent overshoot. This is very important. That is percent overshoot. Okay. Why is it percent overshoot? Because my steady state value has to equal 1. If you're given a problem and its steady state value is not equal to 1, what do you need to do? You need to normalize it, right? So if this was going to be equal to 0.7, then you have to divide your expression by 0.7 to normalize everything to 1. But this is normalizing everything to 1. Okay? So we got 4 equations here. We've got peak time, we have percent overshoot, and we have settling time. We don't really have an expression here for that, the rise time. We can develop one. But usually the settling time, peak time, and percent overshoot are the most important ones that we have. So out of those 3 equations that I see here, if I gave you a problem, which would be the best equation to use to start to analyze your system or define your system? If I said, I need you to design a system that has these 3 parameters, my peak time is equal to 5, my percent overshoot is equal to 20%, and my settling time is going to be equal to 22. Which equations would you use to start? Because you got to design this, right? Your system is going to be a second order system that's going to look like this. That's all you got. So now I need you to design a system that meets those specifications. Which 3 equations of the 3 equations would you use to start your work? Peak time? Anybody else want to vote with Avery? Mason will? Hanson, anybody else? Anybody want to use percent overshoot? Anybody want to use settling time? One brave person. Anybody doesn't know? All right, perfect. So you all are pretty good at algebra, right? If I asked you to solve for a variable, how many equations would you need to solve that variable? You remember the expression, one unknown means you need 1 equation? So you all said either that one or that one. I gave you T sub P and I gave you T sub S. When you do your work, isn't there omega sub n and zeta, which are unknown in both of these expressions? It's 1 equation. How many unknowns? 2. Isn't there only 1 equation, 1 unknown there? Wouldn't you be better to use the percent overshoot equation? You at least can get zeta. And once you get zeta, then you can plug that in for a firm approach there. All right. Since I know you're whizzes at algebra, what's the equation for zeta? This is a tough one, right? Because you got E to this to that and all that stuff. It can be a lot. So I'll help you as best as I can. So I'll go with percent overshoot is equal to 100 divided by E to the zeta pi over the square root of 1 minus zeta squared, right? Now I'm gonna get rid of my 100. So overshoot is equal to 1 over E, and I'll just be lazy and do that. Okay. Now I'm gonna move the E to the other side and the overshoot to the other side. So E to the whatever is equal to 1 over the overshoot, right? Take the natural log, and now I've got zeta pi over the square root of 1 minus zeta squared is equal to the natural log of 1 over the overshoot. Multiply both sides by that. Okay. And we know that the overshoot, so any of you math geniuses would say, hey, Paul, overshoot, 1 over overshoot is going to be a number less than 1, which means this is going to end up being a negative number, correct? Except if it's an underdamped system, the overshoot is going to be between 0 and 1, right? It's always going to be this. So this number over here is going to be greater than 1, isn't it? So that's how it works out. Nobody wanted to catch me on that? All right, so I'm doing pretty good. Now what do I need to do? What should I do? How about I square both sides, right? So zeta squared pi squared is equal to the natural log 1 over the overshoot squared times 1 minus zeta squared. I'm going to bring the zetas to the other side. Zeta squared pi squared plus the natural log of 1 over the overshoot squared times zeta, whoops, times zeta squared is equal to the natural log of 1 over the overshoot. That whole thing is squared, right? I should make sure that that's all squared. So now I'm going to factor out the zeta squared. And finally, did I do okay, Wyatt? We get the algebra right? It's a lot of algebra to get there. So you should just write this equation down. I don't expect you to do this on your own. This is just something that you need to be able to just write down. Okay. So it's algebra, and algebra is not hard, but there's a lot of stuff to make this work, right? So for what it's worth, you may want to just have this in there, or check my work if you want to see the algebra process and see if you can do it. It's a pretty helpful one to do it. But the reason why we do this is I've solved for zeta. I know what zeta is equal to at this point. So now I can use either equation. I can do settling time or I can do peak time to solve for my omega sub n. Once I have omega sub n, I have the full quadratic equation, don't I? Not quadratic equation, the full polynomial. I know s squared plus 2 zeta omega sub ns plus omega sub n squared. So that's my design. All right. So here's the kind of the process for designing your systems, if you will. Do that first. Solve the overshoot equation first. Once you have that, then you can decide if you want to do peak time or settling time. I personally would use this one because it's pretty easy to calculate omega sub n once you know what zeta is. Over here is a little more work, not a huge big deal, but you got a natural log term in there, so you can use whatever you want. Okay. And then how does this show up on a pole zero map? Because again, this is really important to us from a design perspective. because some of the things we want to do is look at how long things are going to take to reach steady state and what's the overshoot. Well, let's plot our poles and our zeros. Remember, when we did the poles and zeros, we had minus zeta omega sub n plus or minus the square root of, well, it's omega sub n plus zeta squared minus 1. That was when we did the quadratic equation with our zetas and omega sub n's. And then we ended up modifying it a little bit when we had a complex number. We end up with that. So if we want to plot those on our pole zero map, our real part is here. And our imaginary part is here and here. Okay. So now we have the values on a pole zero map. Let's go ahead and do a little bit of math to solve for the hypotenuse. So the hypotenuse is going to be equal to, and we'll just call it h for lack of a term. It's going to be the square root of negative zeta omega sub n squared plus j omega sub n 1 minus zeta squared, that term squared. Okay. Everybody see that? Let me go ahead because I'm running out of space. Let me just copy this over on the whiteboard. Okay, so now let's square it. So this becomes the square root of zeta squared omega sub n. Negative is just going to be zeta squared omega sub n squared plus j squared omega sub n squared times 1 minus zeta squared, right? Everybody okay with that? What is j squared equal to? -1, isn't it? So this becomes minus, let's see, omega sub n squared times 1 minus, oops, zeta squared. And when I end up multiplying and canceling things out, I end up with omega sub n squared, which is equal to omega sub n. So that's my hypotenuse. It's just omega sub n. And then theta is just going to be equal to, Oscar had a heap of apples, so it's going to be equal to the sine, the cosine, because we have here and we have the hypotenuse. So it's the inverse cosine of our zeta omega sub n over omega sub n. So that's just equal to the inverse cosine of zeta. So if I'm asking you for, getting some information and I tell you I want a characteristic that's going to give me a pole in that location, then you should have enough information to calculate theta, which, boom, allows me to calculate zeta. All right. So you can either do it one of two ways. I can tell you what the percent overshoot is, or if you have a pole zero map, you can pick your operating points that you want, and then you can start to calculate zeta, and you can back calculate all those terms that way. Okay. So that's how I ended up with that term there. And then if you go ahead and if you use your omega sub d, not your omega sub n term, you can simplify these equations quite a bit. Here's our peak time. That doesn't change. And we didn't have a settling time before. Now we have a, no, did we have a settling time? Rise time we didn't have. Here's our settling time written as a function of that. This term is usually a little bit easier to solve, usually. All right, I think this is the last slide. So if you want to do some design, if you want to move your poles in the vertical direction, which means start here and go up and away from the real axis, what ends up happening is your frequency is going to increase because this is no longer J1, it's J3. Your frequency increases, but the real part here hasn't moved out. So it's still e to the minus AT. So it's the slope here of that exponential does not change. It just means that you oscillate faster than before. Okay, so your overshoot will increase, but then your rise time decreases. So it takes less time to go from 10 to 90% and go from there. If my poles go further away from the real axis, what ends up happening? It's going to dampen out faster, right? Because our time constant is going to be a bigger value, sorry, a lower value. So it's going to reach steady state at a much faster rate. And it's not going to overshoot quite as much. If this here, and remember, this is constant, our damping ratio doesn't change at all, right? Because the inverse cosine, that angle never changes. But what ends up happening is you reach the same overshoot, but it just takes longer period. Why does it take longer? Because the real part has moved out. Our oscillation frequency changes a little bit, but not an incredible amount. So here's the last slide. So if you actually were given some parameters, you can go ahead and you can see how I can calculate it given from any pole zero map. And you can see this is J7 and -3. So I take the inverse cosine. Sorry, I take the cosine of theta. So now I'm get the inverse cosine. So if I want zeta, I take the cosine of the angle, which I can get because I know that this is 7 and this is 3. So Oscar had a heap of apples, right? The angle that I get there is the tangent. I take the cosine of the inverse tangent, and then I get a damping ratio of 0.394. To get omega sub n, which is the hypotenuse, I'm just going to add the real part and the imaginary part squared, square root it, and I get that value there. Now I can calculate peak time, how long that system takes to reach peak time, 0.45 seconds, what its percent overshoot is going to be, 26%, and then how long it takes to settle just by running through those equations. And all I'm looking at here is a pole zero map. I'm not looking at the function in the time domain, and I can calculate all those parameters. You remember at the beginning of the class and towards the end of last class, I said, as much as we can, stay in the Laplace domain because it's a lot of work to go from the Laplace domain to the time domain. These are all time domain parameters that I got just by getting the poles of the system. I can tell you all that information. Okay. Questions on how to do this stuff? Because now you have enough information to do the homework. Let's take a look at the homework. See if I can give you some clues. Let's see. So this is homework number 4, right? I think it's homework number 4. Oh, no, it's homework number 5, right? It's homework number 4. Oh, this is the other homework. So this one should be due on Thursday because this is an easy one. This is just based on those. So this should be homework number 5. So I can post this today. Come on. Yeah, this is homework number 5. So you have a first order system Then you have a second order system because I want a percent overshoot of 15% and a settling time of 2 seconds. I'm giving you 2 design parameters. You have to go ahead and give me the system transfer function. So these 2 are new. This one's pretty simple. Hopefully you see it's pretty simple. This is just taking the roots function and coming up with the roots of that. Over here, use the equations for rise time and settling time for a forced order system. Over here, use the percent overshoot equations and the settling time. And I even set you up so you calculate zeta first because I gave you percent overshoot. And then go ahead and calculate with settling time. And then a bunch of suggested problems to go ahead and do that. So I should post this so that you have that available. Okay. In MATLAB, you can have, and I think we went over this already, you can, there's if you have the controls systems toolbox added in, you can set up a transfer function. It'll display the output and it'll calculate all those parameters for you. I'm trying to remember, let's see, I think it's step. I think if you use the step function, if you have the control systems toolbox set up. Okay, wake up. So if you have a transfer function, you can see that it'll actually compute the step response of a dynamic system. You can do it that way. So all you have to do is pass it a transfer function. So remember we did the transfer function approach. So you can pass it that value and then you can see the results. But it responds with y of t. And then what's the other control systems block? There's another one that you can start. Let's see. Bear with me while I try to pull that up. One moment, please. AI fell asleep. So much for super duper speed response. I guess we go over here. Plotting system responses. I have to look for it. I can't remember what it is off the top of my head. But if you go here, you can see the step and then you can do subplots. Yes, I do. Answer these questions right now. And then you can go ahead, but I thought that there was a definite, and it's in one of the labs, I believe, it'll actually show you how to get those values. I just can't remember the name of it off the top of my head. Let's see if it's under control systems. I don't want Bodie plots. Is it the linear system analyzer? I don't think it's this complicated. I'll have to look at it, but there is a system that you can go ahead and you can just type unit and it'll just go ahead and display it. I just don't remember what it is off the top of my head. So, but if you wanted to check that, you can. Okay. Thanks for those of you who have your screens on. I always like seeing smiling faces. Any questions? Because I'll post homework number 5. You have a homework due Thursday. When would you like homework number 5 due? A week from today or a week and a half from today? Whatever. If you want it, it can be due in a week. Okay, I'll make it due in a week and a half, so it'll be due a week from Thursday. You have lab tomorrow, which is again a little bit of control system stuff. And yeah, onward and upward. Any other questions? All right, have a great day. See you around. Take care, everyone.